Bismillahirrahmanirrahim. I am Dr. Muhammad Adnan, working as Assistant Professor in the Department of Physics, Kohat University of Science and Technology. I welcome you to the course PHY 103 Waves and Oscillations. Today I will be covering the 21st lecture of this course, and the topic is sources of musical sound. You will see this topic with different names. For example, in some books you will see the standing waves in organ pipe. So they are just the same thing. First, I will give the learning objectives. At the end of this presentation, the student will understand that how standing wave patterns for string waves, they will be able to sketch the standing wave pattern for the first several acoustic harmonics of a pipe with only one open end or with two open ends. That is, before this lecture, previously we have discussed the standing wave patterns for the transverse waves on a string, but now in this lecture we will see how one can discuss the physics of standing waves which are related with the sound waves, and those sound waves can be those standing waves can be produced in open organ pipe and also in the closed organ pipe. Also, they will be able to understand the sound waves pattern, which are known as the standing waves. They will relate the distance between nodes and the wavelength. If you remember, in that lecture, standing waves on a stretched string, we have discussed the nodes and antinodes, and we concluded that the distance between two nodes is lambda by 2. Nodes are those points where the element of the rope was having zero displacement. So that the same concept will be used here for the standing waves of sound. Also, they will be able to identify which type of pipe has a even harmonics. That is, we will discuss both the open organ pipe and closed organ pipe, and we will discuss the various overtones. Also, for any given harmonic and for a pipe with only one open end or with two open ends, they will be able to apply the relationship between the pipe length, the speed of sound, the wavelength of the sound waves, and the harmonic frequency and the harmonic number n, and they will be able to calculate either of these by applying the relationship. In this course, we are following the book Fundamentals of Physics by Holliday, Resnick and Walker, 10th edition. In this lecture, we have taken some of the figures and illustrations from this book. Before going into the standing wave patterns in the organ pipe, first we will see the various sources of the musical sound. So generally we can say that musical sounds can be set up by oscillating strings, such as the instrument known as the guitar, the piano, the violin, and also the various kettle drums and snare drums, the air columns such as fluid pipe organs, the wooden block or steel bars, the marimba, the xylophone, and many other oscillating bodies, so that to produce the musical sound. Now we will discuss the basic principles of all these things in this lecture. Now, most common instruments involve more than a single oscillating part. Now, if you know that standing wave can be set up on a stretched string that is fixed at both ends. If you remember, we have discussed standing waves can be formed on a stretched string if we have two identical waves traveling in opposite direction, having same amplitude, having same wavelength and frequency. These traveling wave can give rise to standing wave patterns. Now, in the same manner, we will discuss those standing wave patterns for the sound waves. Now, they arise because wave travel along the string are reflected back onto the string at each end, and hence they form those different oscillating elements of the ring, such as called as the nodes and anti-nodes. If the wavelength of the wave is suitably matched to the length of the string, the superposition of waves traveling in the opposite direction produces a standing wave pattern. We have discussed these things in detail for the standing wave on a stretched string. So we will be using the same concept for the sound waves, but remember, roughly speaking, the sound waves are longitudinal waves, and we will be treating it in a manner that we will discuss in this lecture. The wavelength required of the wave for such a match is one that corresponds to the resonant frequency of the string. We will see this in this lecture. Now, the advantage of setting up standing wave is that string then oscillate with larger sustained amplitude, pushing back and forth against the surrounding air and thus generating unnoticeable sound waves with the same frequency as the oscillation of the string. Now that sounds this production of sound is of obvious importance to say as a guitarist. If we just make the same terminologies that we have used for the standing wave on a stretched string, one can have such standing wave pattern for the acoustic waves. Now, after that background, we can set up standing waves of sound in an air-filled pipe in a similar way that we have discussed on a stretched string. Now, a sound wave travels through the air in the pipe. They are reflected at each end and travel back through the pipe. That is in a similar way that if we just fix one end of the rope and we just oscillate the rope so that to produce those transfer waves, the waves at the far end, which is fixed, the waves will be reflected and there is a standing wave pattern. So in a similar way, inside the pipe, sound waves will be reflected back in the pipe and standing wave patterns can be formed. The reflection occurs even if an end is open, but the reflection is not as complete as when the end is closed. That we will see in the two cases. In the first case, we will discuss the two open end organ pipe, and then we will discuss the standing wave patterns of organ pipe in which one end is closed and the other one is end. So we will see how reflections are possible in all those two cases. If the wavelength of the sound waves is suitably matched to the length of the pipe, the superposition of wave traveling in opposite direction through the pipe set up a standing waves, as we have discussed for the rope. In a similar way, if there is a properly matched such that the wavelength is matched with the length of the pipe, we can have these nice patterns of sound known as the standing wave pattern. The wavelength required of the sound waves for such a match is one that corresponds to the resonant frequency, as I have discussed on the previous slide regarding the transverse waves on a stretched string. So in a similar way, that match corresponds to the resonant frequency. The advantage of such standing wave is that the air in the pipe oscillates with a larger sustained amplitude, emitting at any open end sound waves that has the same frequency as the oscillation in the pipe. So this is just we are just making similarities between the sound waves and with the previous slide over which we have discussed the same thing. This emission of sound is of obvious importance to say as organist, the person who play that organ pipe. Now, as I told you, we will be discussing the standing wave pattern for the acoustic mode in two ways. The first one is that if we have an organ pipe that is having two open ends, such that the pipe is just hollow from inside, so that there is a medium, say air inside, and both ends are open. Now, the simplest standing wave pattern that can be set up in a pipe with two open ends is shown in the figure. This is an antinode across each open end as required. If you remember that in a similar way that one can describe as a transverse displacement, or the pattern for the standing wave for the transverse waves, if we just see here that this is just the cross section of that open pipe, which is open on this side and also on that side. When we were discussing the standing wave pattern on a stretched string, we have discussed that those end which is fixed of that string, over that point there will be a node, that is that will not be oscillating. So in a similar way, here both the ends of the pipe is open, but before discussing those antinodes and nodes, let's see, we know that the medium inside, which is air, these dots are just the representation of the air molecule. For example, they will just oscillate tangentially, longitudinally, in which the wave is traveling. The wave is traveling along this organ pipe, which is open at both ends, since we are discussing the organ pipe with two open ends. So the both ends are open and the air molecules are just oscillating back and forth because the sound wave is traveling across this organ pipe. So you see, if we just produce such a sound inside, that is some part of that air inside is just stationary. If you remember, nodes are those points which is having zero displacement. So when we were discussing the nodes on a straight string, so we were saying that the transverse to the propagation direction, they were having zero amplitude. So now we will say that they are not moving tangentially. So and we also discussed that antinodes are those points which are having maximum displacement. So here the medium particle here are just oscillating with their maximum amplitude, and here again see, this is minimum and then this is the lowest amplitude. And if you remember we concluded there that the distance between two antinodes or two nodes are lambda by 2, and the distance between an antinode and node is lambda by 4. So using the same way as we have discussed on the previous slide, that we will be having a match between the lambdas and the length of the pipe. So in this way we will be discussing the various fundamental and overtones. So there is also a node across the middle of the pipe. That is, if we just produce such a sound, that is, we have a node inside in the middle. The easier way of representing this standing longitudinal sound waves is known as the standing waves. The fundamental mode is here, that once we have just a single node here. This is just a similar way if we have a string which is fixed at the two end and we just plug it from the middle. So in that way the two end will be having node, and in the middle you will be having an antinode, so that length will be equal to half lambda. So in a similar way we can work out with this tangential motion now. So for it to be set up, the sound waves in a pipe of length L, we have that pipe which is open at both ends of having length L must have a wavelength given by lambda by 2. If we see here, we know that the distance between two antinodes is lambda by 2. So this is also equivalent to L. So L is equal to lambda by 2 because at the two far ends we have antinodes. So the distance between two antinodes is lambda by 2. So that this lambda will comes out to be 2L, such that the wave which is traveling, and that will be having a wavelength equal to half lambda inside. And in a similar way we can have these different patterns, such that to produce another wave which is having the same speed, but since the lambda is now different because now we are having another node inside and we have another node inside. So if we see here, we know that the distance between two nodes is lambda by 2. So and we know that the distance between a node and antinode is lambda by 4. So this is an antinode point, this is an antinode point, because that is open. So open end will give rise to these antinode points where the amplitude of the oscillation of the air molecules will be maximum, so that from this antinode to node we have lambda by 4. Again we have distance between two nodes, and we have another distance which is lambda by 4. So if we just combine all these distances, and that is equivalent to L, we will be having an expression like this, such that if we see here, we know that the distance between the two node is lambda by two antinode is lambda by 2. So in the same way we can work out with these overtones. So more generally, the resonant frequency for the pipe of length L with two open ends corresponds to the wavelength. That is, so in this way we can find out the various overtones. So such that lambda, which is equal to 2L over n, where this n is the harmonic number. And as I told you that inside, if the medium is the same, that is the let's say in this case we are talking about air inside, so the speed of the wave, or we can say the speed of the sound waves, will remain the same. So the lambdas are changing because for different harmonics we have different lambdas, and once lambda is changed, that means the frequency is also changed. you see in the first case we have different lambda, for the second we have another lambda. The L remain the same, but the lambda for these different sound waves is lambda is different, so hence the frequency will also be different. So in that way we can find out the various harmonics of the sound waves which are there inside the organ pipe with two open ends. And these patterns can be visualized. Here the patterns are transverse, shown in the transverse nature, but actually it is based on these medium molecules vibration. Now if the organ pipe is designed in such a way that one end is fixed and one is open, so we know from the discussion of standing waves on a stretched string that once you have a fixed end, so that over that there will be zero amplitude points. So that is the nodes. So this will be node, this will be node, this will be node for all these sound waves propagating with different lambdas inside, and it give rise to the various tones. So these will be the nodes. So now we have a figure as shown, some standing wave pattern that can be set up in a pipe with only one open end. This one is open, so we know that open end is anti-node point. So we know that the distance between a node and anti-node is lambda by 4. So in that way we can work out the wavelength for this fundamental frequency. As required across the open end there is an antinode, and across the closed end there is a node, as I have discussed. So in this way the simplest pattern requires sound waves having a wavelength given by lambda is equal to L by 2. As I told you, the length of this pipe is L, and we know that the distance in terms of lambda between a node and antinode is lambda by 4. So this L is equal to lambda by 4, so that lambda is equal to 4L. The next simplest pattern requires a wavelength given by L is equal to 3 lambda by 4. So this is 3 times now. If we see the distance between the node and a node is lambda by 2, and then you have another node and antinode, their distance is lambda by 4. So if we work out, you will see that this will be 3 lambda by 4, and that comes out to be lambda will be equal to 4L over 3. Now if we see, there is a node, and here we have an antinode because of the maximum displacement. So this is what? This is a node and antinode distance is lambda by 4, and again we have an antinode and node lambda by 4, and then we have a node and antinode lambda by 4. So how many lambda by 4 are there? 3 times. One started from here to here, we have 1 lambda by 4, then from here to here 2 lambda by 4, and then from here to here 3 lambda by 4. So that's why we can find out. And similarly for this one, if we see, this is a node because this end is fixed. So from here to this maximum amplitude point, which is antinode, so we have from here to here lambda by 4, then lambda by 4, then 3 times lambda by 4, 4 times lambda by 4, and 5 times lambda by 4. So for this we have the 5 times lambda by 4, and hence the lambda will comes out to be 4L over 5. So more generally, the resonant frequencies for the pipe of length L with only one open end. Remember, for the 2 open end and for the 1 open end, the frequencies and these lambdas and these frequencies and lambdas are different. So in that way one can find out the wavelength for various harmonics. And if you see for one open end organ pipe, we have only the odd harmonics which are possible, the evens are not possible, in which harmonic number n must be an odd number. The resonant frequency for all these wave modes are given by this expression, as we have discussed for the two open end situation, that since the medium inside is the same, so the velocity will be the same, or you can say the speed of the sound inside the medium will be same. The lambdas are different, as one can see that for this fundamental mode lambda is equal to 4L. For the second case the lambda is decreased, so once the lambda is decreasing that means that the frequency will be increasing. So in this way, such that the velocity will remain the same. So one can find out the various harmonics inside these organ pipes, which are essential components of the sources of musical sound. Now if we see here, these frequencies for the two open end is given by this expression, and the frequency for all the various fundamental and also the overtones are given by this expression for the one open end organ pipe. Now the important thing, we have discussed all these parameters, the frequency, the speed, the lambdas. Now we'll see what is the role of this length, or we can say the length of the organ pipe. The length of a musical instrument reflects the range of frequencies over which the instrument is designed to function. You see, if this L is small, that means that is designed for smaller frequencies. If L is large, so that this will be let's say if all the parameters are the same, the overtones for the given overtones, if we see if L1 is small and L2 is large, so if for the larger one of the instrument which is made large, the frequencies will be smaller. So that we can see, and smaller length implies higher frequencies, as we can see if we just divide this with smaller number, so that means the frequency will be large. If we divide it with large, from mathematically it is clear. And also if we see the length of this pipe, if it is this large, it will give rise to more than the lambdas will be keep on smaller and smaller, the frequencies will be higher and higher. That's why we have this thing. As an example, we show the saxophone and the violin family with different with their frequency range is suggested by the piano keyboard. This is the suggested frequency. If we see these instruments, this is the smaller one, and and the sizes keep on larger and larger. And also for the case of violin as well, we have a shorter one and we have a larger one. As we have discussed, the sizes does matter for the resonant frequencies in either of the organ pipe, whether the one open end or with the two open end instrument. Now the net waves in any oscillating system that give rise to a musical sound, whether it is a violin string or the air in an organ pipe, the fundamental and one or more of the higher harmonics are usually generated simultaneously. Thus you hear them together, that is the superimposed as a net wave. So with different instruments are played at the same node. By node, we have discussed the various mode on the previous slide. They produce the same fundamental frequency but with different intensity for the higher harmonics. Now based on this topic, which is the standing waves pattern regarding the sound waves, you need to go through this part of this assignment, which is based on this problem given in the module 17.5. And with this, I thank you for your time.